Okay, I think, hi, I think I'll start, although we have a bit of a thin attendance. Um, um, so let me start. Yeah, I'll record it for the benefit of people who didn't show up. But why don't you guys? I know thank you for showing up online. I know that most of you expressed. Can you hear me all right? You have to tell me. Can you
Yeah,
hear? Okay. Yeah, so do ask questions. So don't, since although I know it's a little bit hard to do it online, but do stop me and ask questions. Even if, so others who who would be listening on a recorded thing can benefit from your questions. So hopefully. Yeah, I will be discussing Reluplex today, which is a decision procedure specialized to work for verifying properties for feed-forward neural network with the ReLU activation function. Now, the reference material for this is this paper, okay? This decision procedure is implemented in the tool called Marabou, which has an SMT solver like Z3 with this special Reluplex integrated as one of the decision procedures the inside Marabou. Now, so I just wanted to, I think this is the only paper. I don't think this, for this material. Um, so you will have to rely on this if you have any doubts and, for your reading. But before that, I want to, there is a slight difference in the way that simplex is presented in this paper when compared to the way that I presented in the last lecture. So I want to, show the difference. Actually, the way it is presented here is, in some respect, is better to illustrate. Okay, so that I will do and answer any questions or doubts that you may have on simplex before I start describing the Reluplex algorithm. Okay, so this picture is familiar to you. Okay, so we already discussed this example to illustrate the simplex procedure as to how it zeroes in to a satisfying solution, using this pivot and update operation. And the algorithm, that I showed was exactly what is listed here. Now, the same algorithm can also be, described uh, as in terms of application of a, a set of rules or inference rules. Okay, it can also be described that way, and sometimes it is informative and intuitive to view the procedure being described as application of a set of rules. And since the Reluplex procedure is described in terms of these things, and I wanted to introduce simplex in terms of these inference rules. So Reluplex is, I'm sorry, simplex. So simplex has like this pivot and update. Here, the pivot and update, that combined operation is split into two pivot operations and an update operation. Okay, the pivot operation just so all the rest are the same. So you have a basic set of basic variables and non-basic variables. Okay, and you pivot whenever you whenever there is a basic variable which violates its one of its bounds. Okay, then you pivot. Okay, the pivot operation itself here is there are two pivots. One for the case where the violation is at the lower end, at the lower bound, or the violation is at the upper bound. Okay, those are the two things. And because and here the pivot operation just pivots the two variables. It moves a variable in the non-basic set into the basic set, and it flips it with something with the basic set. So it chooses, it first identifies a variable in the basic set that violates a bound, and then picks a variable in the non-basic set, a slack variable. So, which, as I explained, you can have, if the slack is positive, then it picks a variable, a non-basic variable that can be, adjusted to increase the basic variable to fix its violation. So here, that is what the pivot up, the two pivot rules says. There's one for the case where the basic variable violates at the lower bound end, and the other case where it violates near the it violates its upper bound, and the set of slack variables from which you could choose to adjust its value to fix the violation is defined as slack plus and slack minus, which is exactly the condition that is checked in this algorithm in line 7 and 12. And the update operation is described separately. So the update operation just determines the exact amount that needs to be added or subtracted from the non-basic, the slack variable, in order to bring the basic variable which is in violation to either its lower bound or upper bound, and that's the delta that it computes, and then it updates the leaving non-basic variable xj. So that is shown here separately. And then there is two rules to check if you've reached you terminate with a failure or terminate with a success. Okay, so if you still have one or more basic variables which are violating their bounds, and there are no appropriate slack variables, either plus or minus slack variables in the non-basic set that can be used to adjust and fix the violation, then you return unsat. And if there's no basic variable, no variable in the basic set that or every variable in the basic set satisfies their bounds, then you terminate with success. Okay. Any questions here? I hope you understand how you need to read these inference rules. It's just these these are some of the operations that are done at various lines in this set, okay? And your procedure is described as applying one of these inference rules until you end up getting a failure or a success. Okay. So I will illustrate the application of these inference rules, okay? And these tables that are shown here is also, in some sense, easy to follow. It makes it easy to follow the simplex procedure. So this table here first shows, in the columns, the variables, the list of all variables. First, the non-basic variables, which to begin with will be exactly the primary variables, x and y in this case. And after this double bar here in the table, these the S1, S2, and S3 are the basic variables, which at the start of the simplex procedure, will be the slack variables. Okay. And so we the other three rows, show the lower bound and the upper bound for each of the variables. And the middle row here gives the current assignment to all the variables. And the tableau, the equations in the tableau are described on the right-hand side. So, okay, there is one small, what I'd say is a technical detail that in the way that the Reluplex paper describes the simplex is slightly different than the way that I presented it last time. So, for example, if in this case, you notice that there is a constraint on the imposed on one of the program variables itself. Here, x in this case. It is quite possible. I mean, in the way that I presented it last time, I assumed that all the program variables were unconstrained, that they're bounds from minus infinity to plus infinity. But you can have cases because, I mean, there I was assuming that even if there was such a constraint on one of the program variables as shown here, you could still create a slack variable to equate that to that program variable and then transfer the constraint on the primary variable onto that slack variable. I mean, that unnecessarily creates what might be considered as redundant additional variables, which are the slack variables. Instead, there is a slight, you can tweak the simplex procedure. You could keep, you don't need to keep, have a new slack variable corresponding to x to take care of this constraint on the x variable. But what you can do is, right at the beginning of the simplex procedure, you see if any of the program variables have any constraints, and you can fix them right away, okay, to bring them to their respective bounds. This is it's as though you're changing the initial assignment. You make it such that all the program variables, the constraints on the program variables are satisfied, and that's what you can do. So that eliminates the need to have additional variables redundantly equated to simply one of the program variables, and that's what is done here. Okay. So that so that's the only case when you have the update operation that is shown. You update the non-basic variables right at the beginning, and then as a result of doing that, you see that one of the bounds, one of the bounds on the basic variable S3 gets violated because the value of S3 becomes -2. It violates its lower bound. Then you pivot that, okay? Pivot S3 by choosing a non-basic variable. So here, of course, that has to be done as per the variable ordering, which I haven't shown here. Okay, I'm kind of going through this example only to illustrate this table so that you get acquainted with this table, which I will then reuse when I describe Reluplex, and that's the reason I'm going through this. Okay, so what happens? Okay, so you know, as a result of this, what you do is you have to update y in this case. I guess that is what is shown. Okay, S3 is basic and out of bounds. So we pivot S3 with y. Okay, which means, and by adjusting y enough to bring to fix you know, the value of S3 to bring it to its to increase it to its lower bound. Okay, you know, so that as a result of that, you you know, you pivot. So S3 becomes moves into the leaves the non-basic set and enters the basic set, and y enters the thing, and y will have its value assignment adjusted by the delta in order to bring S3 to its lower bound. Okay, and then you know, once you pivot, all the equations in the tableau gets changed so that yeah, so the and all the new values for the other you know, basic variables will have to be computed and updated, and the assignment has to be changed as per the new equations, and that's what you know, that's how you know, the simplex proceeds. Okay, and in this case, and at each step after pivot application of the pivot and update rules, you will have to check if you have success. If not, then you will have to pivot again. So in this case, you know, with that, with the single pivot operation, you know, all the variables satisfy the respective bounds, and therefore you get a set. Okay. So any questions or doubts about this tabular notation? Any of the inference rules? Okay. Oh, I see. No. Yeah. I'm here. I'm just showing another possible thing. Okay. So if the variable ordering were different, and like you know, x was before y, it's also possible to pivot S3 with x, in which case you would get the state. So what I've shown here in this table is pretty much the configuration or the state of the simplex procedure after each you know, pivot and update operations, application of the pivot and update rules. Okay, so that's what I'm illustrating here. Yeah, so this is a question that I raised yesterday. So before I move, I will just summarize. I'm not going to give the whole proof of the termination of this algorithms and why you know, when it terminates with an answer that it is a sound answer, but I'll give you a little bit of intuition about why simplex works correctly. Okay, the main observation is that if an LP problem instance, problem has a satisfying instance, then it always has a solution that with the following structure. Okay, that there is always a solution, and that is the there is a solution with this kind of a structure, and that's what simplex. And there are only finitely many such solutions among the infinite set of satisfying solutions for the LP problem. And this one, so this special kind of that has the structure here. This is a solution where some subset of the non-basic or the additional variables, that is the slack variables, are set to some subset of the slack variables, not the primary variables, are set to either their lower and upper bound, and all the rest of the variables, including the program variables, all the rest of the variables, that are not in the subset of the slack variables, and the rest of the program variables are actually defined as some linear combination of these variables that are set to their lower and upper bound, as per the equations in the tableau. For example, here C is here. There are two such solutions that follow this structure. C is one, which is the intersection of S3 and S1, and there is this intersection of S2 and S1 where I'm pointing the cursor to, which is that point is not named. That is not named in the picture, but that is what I call as E, are both solutions. Okay, and you will see in the solution C corresponds to where S3 and S1 are set to their lower bounds, whereas the solution E corresponds to which is the intersection of S2 and S1, corresponds to the case where S2 and S1 are set to their lower bounds in this case, and X, Y, and the other things are determined as a linear combination of these things by plugging them into the equations. Now, there is also another intersection point of S1 to S3, which is S3 and S2, which is right here where I point the cursor, which I've named as F, and that is not a solution. So not all combinations of these intersection points are necessarily solutions. Okay, so you can even sometimes have a solution in which only one of the slack variables are set to the lower bound. For example, if the line S1 were to be moved all the way down, okay, to its all the way down, such that it includes the point B or if S3 was moved all the way down to include the point which is labeled as B, then this B itself will be a solution, and that is not really an intersection of two things, but it is just lies at the intersection of S1 and B. So that's a solution in which only S1 is at its lower bound. Okay, so it's also possible that the solution solutions in some solution that simplex produces, only a single variable is set to its lower and upper bound. So, but the thing is that some subset, non-empty subset of this S can be, there is a solution always where some subset of the slack variables are set to their lower and upper bound, and the rest are expressed as linear combinations of the thing. Okay, and simplex always satisfies. There is an invariant, that is, after every application of pivot followed by an update operation, the following invariant always holds good, okay? And that is every variable after you pivot, every variable in the current non-basic set always satisfies its bounds. That is true at the beginning as well as after every pivot operation. Okay, that's that's another observation that one can make. Okay. Okay, further observation is when you have multiple solutions, like in this case, in this example, the point C and point E, which is the intersection of S2 and S3, both the solutions, okay? And you can see that the solution, you can actually derive the solution E from the solution S3. So it's just that you just have to, the C and E are solutions. E can be expressed by actually pivoting the appropriate variable. So you can actually express, derive E from as a linear combination from C by just pivoting S3 with S1, because C is the intersection of S1 and S3, and E is the intersection of S1 and S2. So S1 and S2, so you can actually get that, the E, by just pivoting S1 with S2. So they're all linear, all the solutions. One solution is a linear combination expressed in terms of another set of slack variables. Okay, so that is also is true. And these observations are important in understanding why simplex works correctly. Okay, soundness, as I said, of any decision procedure is concerned with when the procedure terminates, whatever answer it gives, either a satisfying solution, or if it says unsat, then if it says yes, then the satisfying solution it gives indeed is satisfied by all the satisfying all the inequalities in the problem. The others is when it says no, then indeed it is unsatisfying. Now, part one is quite obvious, okay, because the invariant always ensures the invariant that the non-basic variables always satisfy their bounds. And so when it terminates, with a yes answer, all of them, all the basic variables satisfy. You terminate only, you give a yes answer only when all the basic variables satisfy their respective bounds. And since all the non-basic variables indeed are always satisfy the invariant, therefore, when you say yes, all of them indeed satisfy the. It indeed satisfies all the constraints. The tough part is the second one, as to why, when you cannot make any further progress, that's when you say it is terminate with a failure and say unsat. Why should that be the case? This is especially because when why this one terminates, we will I will get to. That's a separate thing. But what I'm trying to explain is why when it terminates, why when the algorithm terminates and says it is a failure, that indeed there is no satisfying instances. Okay, instance. Now, of course, there is, the reason that why you can have doubt in this case is because this, in some cases, of course, here, for example, there are two solutions, but the solution C is reachable only by some variable ordering. not every solution is reachable by every program ordering. So you may ask the question, if indeed you choose some program variable ordering in which C is not reachable, where is the guarantee that you can always get to E? So, and the reason is, the intuition as to why that is possible is because the observation that I just now made. The other solution, E solution, can always be expressed as a linear combination of C by actually pivoting the thing. So, so when for every program variable ordering, there is another solution, an alternate solution, which is indeed reachable from is indeed reachable for that program ordering. Okay, and that's why. So in this case, for example, you can reach E by if for in a different program ordering by going from A to this point where I'm pointing the cursor. Okay, and then move to here. Or you can even in another program you can go from A to D, where S3 intersects the x-axis, go to this intersection point F, and then move to the intersection of S2 and S1. So for every given program ordering, there is always a way to reach a solution that is feasible under that particular ordering for some combinations of this slack variable. Okay, and that's the reason why, if there is no progress at all when you terminate, and then it says there is still some basic variables that are violating their bounds, but there is no progress that you can make because there is no slack plus or slack minus. There's no non-basic variable that you can use to fix it. Is indeed a case where there is no there's no satisfying solutions at all, and therefore it's sound to return unsat. So then in that case, it really boils down to why should simplex really terminate? Why you couldn't be forever, indefinitely, and forever be doing the pivot and update operation. And that is relies on the fact that there are only finitely many configurations that are possible. Okay, by configuration I mean something like this. So given a set of non-basic variables, you can always these equations, the tableau is defined uniquely, and since the non-basic variables are always for any given lower and upper bound for x and y, these S1 and S2, the other basic variables are always dependent on that, and therefore they are uniquely determined in terms of L and I. And since there are only finitely many variables with finitely many lower and upper bounds, the number of configurations is finite, and therefore you can terminate. Non-termination is possible only if the same configuration doesn't recur. Okay. Now that can be shown because every time, even if you get in that process, get to the same day, you revisit the same, you get the same set of variables in the non-basic set, you can actually show that you will always, even when it recurs, you will be getting a different assignment. You will never get the same assignment. Okay, either the lower and upper bound assigned to the non-basic variables will be different. It will basically be different, and therefore, and that's why even when you may have at different points the same non-basic set, the value that the assignments for the variables that you get will be different, okay? And that's why they never recur. And that's why simplex kind of it works, okay? So any questions here? I know this is a sketchy proof, but you know, those are some of the key ideas as to why simplex works, okay? Anybody have any questions? Okay. Okay, before I move to start discussing Reluplex, let me, I hope you can read this. I mean, this typed text in here. What exactly is Reluplex is trying, the problem that Reluplex is trying to satisfy, okay? For example, in this, when you're really trying to apply just an LP solver is not good enough to check your properties. Why? Because as you can see that the verification problem that you want to verify will be the formula will not exactly be just is not an LP problem. By an LP problem, I mean an LP problem. By LP, what I mean is just a conjunction of linear inequalities is what I call as an LP instance, okay? Whereas what you want to check when you have to verify that a particular property, in this case, that V31 is between, this is an example, this is again an example that I've already seen. So, what we're trying to show here is if V11, is it possible to have V11 between 0 and 1 and V31 have a value between 0.5 and 1. So in this case, indeed, it is possible. In order to verify such things, what you will end up is the formula that you will have to check, either the validity or the satisfaction is not a simple conjunction of linear inequalities. As you can see here, it has implication as part of the thing, as part of those things, and therefore they are not going to be an implication is basically a disjunction, okay? A implies B is not A or B, and therefore you not only have conjunction, but you have conjunction and disjunction. Therefore, the question is, how do you solve it? Now, you can throw this thing at Z3 because Z3 obviously is able to solve such formulas. Okay. Now we are trying to what Reluplex is a special purpose decision procedure which extends simplex in some ways to be able to handle disjunctions as well. Okay, and that's what I'm going to tell you. I mean, describe here. So, like for example, I mean here. What is consider this formula that I've highlighted, phi, which is not a simple conjunction of linear inequalities, okay? Because you can see that the third conjunct indeed has a disjunction, okay? Read the vertical bar as OR, and this is a logical AND, okay? So this is, you cannot just send it to simplex, okay? Because this is not an LP instance, it's not a simple conjunction, okay? Can anyone tell me if phi is satisfiable? Just want to check if you're all awake. Hello?
Yeah, it's not satisfied.
Who's this? Identify yourself.
It's Romans.
Ah, you said it is not satisfiable, correct?
I hope so.
No, what was your answer? I'm trying to see.
Yes, that was my answer.
That unsat. Yeah, yes, it is, because see, the first two, I mean, in order for this to satisfy, all three conjuncts have to be satisfied. So if x is less than or equal to y and y is less than or equal to z, then x is indeed less than or equal to z, because less than or equal to is transitive, correct? Okay, and so x cannot be greater than z, and similarly, since y itself is less than or equal to z, z cannot be less than y either. Therefore, under there's no way you can satisfy the third constraints under the first two things. Okay, but the question is, how do you, if you were to be just using LP, you can't just throw this problem at LP, because Z3 has some version of DPLL. You're able to do that, but I'm trying to see what is it. What is, how can you just try, if you are constrained to use just an LP solver?
Sir, then I would use x less than equals to y and y less than equals to z and z less than y, and that would be an LP instance. And then the second one would be I would take x greater than z and x less than equals to y and y less than equals to z as two LP instances and try to solve both of them separately.
Correct. Okay, so one way you were exactly said, for every disjunction in your formula, you can split them. Okay, and that's kind of the general thing. I mean, for every disjunction in your formula, you'll have to split into two separate cases. Okay, and these can be, you can see this can get very complicated, right? So you could so that is one way. Like that is a very correct observation. I'll kind of situate the same thing in a slightly different framework. Okay, and this amounts to kind of the same thing, or you could then you could, when I situate it in this framework that I'm going to describe, you will get an aha moment. Okay, that, oh, maybe there are several different ways of doing it, rather than blindly case splitting, because the case splitting method, blind case splitting, can be may not scale, because you have to consider, if there are lots of disjunctions embedded in your formula, you will have to then case split for every possible. I mean, your number of case splits will be exponential in the number of such things. Huh? So, I mean, that will become obvious here. So, what I'm saying is, there is this concept, you can kind of abstract this formula phi into phi prime. So what have I done in phi prime? I've just replaced each inequality in phi, each distinct inequality in phi, with a propositional variable B1. I mean B, okay? So B1 corresponds to x less than or equal to y, B2 corresponds to y less than or equal to z, B3 with the other one, and B4. Now, this is a pure propositional formula. Now, the original, okay, the original formula is satisfied only when this phi is satisfiable, phi prime is satisfiable, okay? Because for this to be satisfiable, you have to have B1 and B2 to be true, and either B3 or B4 to be true, okay? So this is possible in this case. Phi prime is true when B1, B2, and B3 are true, or B1, B2, and B4 is true, okay? So now, this is, I call it as an abstraction, firstly because it is throwing away this, it's hiding the detail that indeed B1 is actually an inequality, okay? This is also an over approximation of the original formula, because whenever you see there are more instances when phi prime is satisfiable than when phi is satisfiable. Okay, if phi prime is unsatisfiable, then certainly phi is unsatisfiable too. Okay, so that's why this, I call this as an over approximation, because phi prime is satisfiable under more number of instances than when phi is satisfiable. Therefore, one way to do is you get this abstraction. I call this as the Boolean abstraction, because I'm replacing the inequalities with Boolean variables. And you solve this. Now, this can be solved using DPLL, because this is a purely propositional thing. Okay. Now, get a satisfying instance of phi prime. Now, for example, B1, B2, B4 is a satisfying instance. Okay. Now, then it's a satisfying instance of phi prime. But just because it is satisfies phi prime, there's no guarantee that it has to satisfy, because phi prime has thrown away some constraints about these inequalities. Okay, B1, B2, B4 is obviously not satisfiable, because B1 and B2 in the theory of inequalities implies negation of B4. Okay, what you can then do is, for every sat instance of this Boolean abstraction formula phi prime, you can then check if indeed it is, that one is a satisfying instance. Now, this is exactly what someone just now suggested, that you can actually do k-split. This is exactly what you're doing, but this gives way. Okay, so Reluplex kind of uses this concept of constructing an over approximation of your original formula that describes, that encodes the DNN behavior, but you will see, in a slightly different way, so that you can delay this k-splitting as much as possible. Okay, and see if you can get a solution even without k-splitting. That is actually possible. Okay, and Reluplex does it inside the simplex framework itself. And that's what I'll show you. Now, you can ask the question, since you can always throw this problem at Z3, what does Z3 do? Now, this is something I've only shown you, but I'm not described in this. I've shown you in picture, like DPLL-T. What it does is, see, one thing is getting full satisfying instances like this, and then separately checking for each of them. Now, that is almost like k-splitting, which is exponential. Okay, because because the number of satisfying instances here of the Boolean abstraction could be 2 to the n. Okay, where n is the number of proposition variables here. But just to mention, before I go to DPLL, Z3 is not going to be doing this a naive k-splitting. What it does is, it does a bit of smart thing, because as it generates this satisfying instance, the way DPLL works is, it generates one, sets one Boolean variable. It gives truth assignment to one variable. So first it says, let's try B1 to true, and then B2. After each point, because B1 and B2 are actually linear inequalities, it tries to see if B1 and B2 actually implies. From that, you can derive some fact about it, some new things. Now, as you can see, if you know that B1 is true, that is x less than or equal to y and y is less than or equal to z, from that you can propagate, and then there's a technical theory propagation. Then you can derive that, since I know that less than or equal to is transitive, and I can derive x less than or equal to z, and kind of add it, just like you added learned clauses, you can add, do what is called theory propagation to learn new facts about, based on the partial assignments that you have so far, and you can add them as learned clauses to prevent, now in this case, if you add indeed x is less than or equal to z, then immediately you see this will reduce to false. Okay, so B1 and B2 implies not of B1 itself B2 implies not of B3, and B1 and B2 implies not of I'm sorry, B1 implies B3, B1 and B2 implies B3, B1 and B2 implies B4 in this case, okay, which you can get by by querying in a clever way an LP thing. So you make you did learn new facts, just like conflict clauses you learned, and that technique is called theory proposition. That's what DPLLT does, and it saves a lot of can reduce a lot of this exponential case splitting, and through this thing called DPLLT. Now, I'm not going to say anything more than that. All the takeaway is that Z3 also has a bag of tricks, okay, which I listed as theory propagation, to avoid exponential number of case splitting. Now, Reluplex is another way of doing it. So this is, I took a slight digression to see how to very briefly give you an overview of what DPLLT is. Now I'll go to describing Reluplex. Any questions? Okay. But as you will see, it'll use this concept of getting an over approximation. Okay. Yeah. Yeah, how do you do this? I mean, this is just an observation that was already made by one of you. You can actually, in this case, all the case splits correspond to, if there are ReLUs, all the case splits correspond to the condition that goes into the ReLU, which I have listed here as ReLU1 and ReLU2. Therefore, what you will have to do in order to convert them into multiple LP instances is, you see, yeah, so for each ReLU you get, you need a case split. Okay, so there are two here. There are two ReLU nodes, and therefore you have 4 case splits with the combination. Just imagine that if you have 1 million nodes, then if case splitting just will be 2 to the million different cases. Okay, and so you just cannot expect such a case splitting method, a naive case splitting method, to scale beyond a few, 100 ReLU nodes, if at all. Okay, so that's why you need to, yeah. And the key idea that Reluplex uses it is what is called kind of a lazy case splitting. Don't case split eagerly like what I do here by just enumerating all the cases, but try to solve it, assuming that maybe there are, ignoring the ReLU constraints. Okay, and how that is done is what I'm going to show you. Okay. Okay, so here I'm expressing this, the formula that describes, okay, pretty much, I'm going to be throwing away, I'm assuming that here the ReLU, I'm throwing away the ReLU constraints. If I throw away the ReLU constraints, that is, if I assume that there's no relationship between the forward and the backward variable that connect a particular ReLU edge, then this is ReLU is the only point at which nonlinearity is introduced in the formula that describes the DNN. right? If you assume that these forward and backward variables connecting ReLU are free variables that have no relationship between each other, then so you could just express them as just linear constraints, okay? And that's what I'm showing here in a tabular form, okay? So as you can see for a DNN, V11 is the input. So each of the internal nodes are expressed as linear combinations of the node prior to that. Similarly, starting with the forward variable, the forward variable, the variable that is the forward variables feed into are expressed as linear combinations of the forward variables of the which are the output of ReLU. Okay, so what I'm doing here is introducing one additional variable. Okay, these are slack variables A1, A2, and A3. Okay, it's pretty much as though I'm throwing away, because I'm throwing away all these conditions. Okay. If I throw away those conditions, then I can easily express, so there is A1, which corresponds to the equation defining the value of V21B. Okay, that's what this is saying. V21B is equal to V11. Similarly, and V22B is equal to, I'm sorry, this is wrong. Correct. V21B is equal to V11, and V22B is equal to minus V11. Those are the expressions, linear expressions that appear. And similarly, V31 is a linear combination of V21F and V22F. And those are the expressions that appear. For each of them, I introduce a slack variable, as you would do when you were converting a formula. Conjunctive formula. So, and that's what you do. Okay. Now the constraints on all these A1, A2, and A3, since they represent just equations, so they just have to be the upper and lower bound have to be 0. Okay, because they always this linear this defines an actual equality, and that's why equality is expressed as with lower and upper bound to be 0. Now, the property V11, there can be property that you want to prove has an assumption on the input variable, and there'll be some constraint that you want to that you expect to hold good on V31, and that's why V11 and V31 have some required bounds in here. Okay, so since we're trying to prove that indeed it is possible to have V31 between 0.5 and 1 whenever V11 is between 0 and 1. So the properties will impose the lower and upper bound on these things. Okay, whereas all these, and there won't be any. Now here, so here you see, I'm not imposing any constraint on V22F and V22B or V221F and V21B. That it's in that sense. So because I'm saying both of them are free to be any value between minus infinity and plus infinity. So it is in that sense. This is I'm saying this is an over approximation of your original neural network. Is this thing clear, or how I got this table representing the original formula?
Yes, sir.
Okay. So now, how do you now? If you solve this, obviously you will the solution will be start with it. That is what we start with. Okay, that is an LP instance because you're throwing away all the ReLU constraints, which are the only source of nonlinearity. So when you solve it, if you do get, if a solution, if there is no solution for this over approximation, then the original, there won't be any solution, satisfying solution for the original network also, correct? Because this includes all the satisfying instances on the original network as well, because this is less constraining than your original network. Now, so then you can say it's unset, okay? Now, if a solution exists, suppose there exists a solution for this over-approximated LP instance of your problem, then it doesn't mean that your original problem is, I mean, that formula which we are trying to check, which is what this is the one, is necessarily thing, because I have ignored the ReLU constraints. It is true on the original network only if the ReLU constraints are preserved. So that you can do separately. Okay, if alpha satisfies all the ReLU constraints, what is the ReLU constraint? It's exactly, you will have to check if the LP solution that you get satisfies, I mean, the ReLU, the variables that define the input and the output of each ReLU node. I call that as the ReLU pair, okay, of variables, the values that are assigned by the LP solver. For that, if they satisfy the corresponding the ReLU constraint this way, okay. So then if they do, then you say it is satisfiable on the original problem as well. Okay. So otherwise, only then you will consider doing the K-split. Okay. That you could do. So that's why I call this a kind of lazy K-splitting. The one central idea, that is the key idea of Reluplex, is you construct a linear over approximation, a certain kind of linear approximation, which kind of throws away all the ReLU constraints to get an LP instance and try to solve it. Okay? And then check individually if they are, then you do case split. But I think it does better than that. Okay, it tries to, what it does is, rather than immediately case splitting, if there are, if you could, if they're already none of the ReLU constraints are violated, then you can declare it as satisfying. But it tries to fix some selected, it tries to fix all the broken ReLU nodes, okay, by making it satisfy its ReLU constraint, either by changing the output or the input, okay, to the in the ReLU pair. It fixes it, and then it goes back to try and see if, because as a result of fixing this broken ReLU pair, you might end up violating the constraints that on the other variables, the non-ReLU variables like V11, V31, and so on. Therefore, you will have to rerun your LP instance. Okay. So, by fixing these values and by fixing the ReLU pairs, if you don't, even after trying this method to see if I can fix as many ReLU pairs, if not all of them, and then you get to a solution up to a certain point, you can keep delaying the case splitting, but if nothing works, then, okay, as a last resort, you split. You pick one of the ReLU nodes, split it into two different instances, and then run this procedure recursively on each of the two each of the two LP instances that you get as a result of case splitting. Okay, so that is what this thing does. Okay, this will, in the worst case, it will delay, tries to delay the case splitting as much as possible to see if you can get some solution by throwing away some subset of the ReLU pairs. And if you can get with only keeping some of the ReLU pairs, then, and you can get a solution, then you don't need to do any case splits. Otherwise, you do case split when it is absolutely necessary. That is the idea. Okay, I will illustrate this on an example, which should hopefully make things clearer. But any questions here? Okay. Before I do that, I'll tell you what exactly case splitting means. Okay, so for example, this is an LP encoding of the DNN and over approximated LP encoding. So if I want to say, here I have thrown away both the ReLU nodes because I'm not constraining the forward variable to be I'm not relating that thing to the backward variable at all. Now let's suppose that I want to create the LP instance corresponding to the case split where the ReLU node, the ReLU pair V21B, two cases where it is less than or equal to 0 or greater than 0. You can easily model this particular version of your thing under this case split by just changing the lower and upper bound of V21B. Okay, V21B, you want to consider the case, solve the case where the V21B is less than or equal to 0. All you need to do is solve the LP instance by making the changing the upper bound of V21B. And the other case, V21B of greater than or equal to 0, corresponds to this LP instance where the lower bound of V21B is changed, okay, to be 0. Okay, so now that is how you do, and then you do it. But as I said, the idea is to try and see if I can solve this without doing the case splitting, and then try to see if I can get a solution even before I actually consider doing this case splitting. Okay, and that's the crux of Reluplex algorithm. Okay, and so first I will illustrate it on this example and then show the actual pseudocode for the procedure. Okay. Now I once again ask, is there any doubt? Any of you has any doubt in saying that this table, which actually models a set of linear constraints with slack variables A1, A2, A3 introduced to denote the linear expressions and the linear constraints, is an over approximation of your DNN, the original DNN. Anybody has any doubt?
At the worst case, we have to split this argon.
Okay. The worst case, tell me.
So suppose we have ReLU set n nodes. So at the worst case, we have to split each nodes.
Yes, in the worst case, I'm not. Yes, see all this in the worst case, they are worst case exponential. Okay, there's no denying. Okay, so in the worst case, you might end up splitting. But here we work with the over approximation to see if you can get a solution without even before you can do a case split. Okay, and that's what I'm going to illustrate. So if your question is in the worst case, this Reluplex will also end up case splitting exponential times. Yes, it's possible. Yes, but the idea is to try and not do it, okay, and try to see if you can get a solution using, without actually doing a case splitting. And you will see in this case, it is possible, okay, without actually doing a case split at all. In this case, yeah, and that'll give you an intuition. You come back to this as to you have to ask. Okay, I will show you that it is possible to get a solution to this without actually doing a case split. And then you can ask the question, why was this possible? Okay, that gives you intuition. Okay, so let's see. Here what we're trying to see, once again, what we're trying to see is we want to make V31. We have to see if the output, we can get some input that can make V31 be between 0.5 and 1. Okay. Yeah, it is possible because you can get V11 to be 0.5 or minus 0.5. So that is what I'm trying to solve this. Okay. So first, there is this is A1, A2, A3 are the slack variables, and these are all the other variables, the input output variables, and the internal variables. Internal node variables are all the primary variables. Now here, right at the start, V31 is obviously the initial assignment. I'm starting with 0 as as we have making the simplex procedure. So at this step, I'm running the simplex procedure. That's all. Okay, on this over approximated LP version of the LP instance, which is an over approximation of your network. Okay, so since this is a primary variable, you fix it. Yeah, so what this does is you're fixing it on 0.5, but as a result of which A3 gets violated, okay? Because if I make V31 to be 0.5, this requires that V31 should be equal to V21F plus V22F, right? But V31, V21F plus V22F is 0, and therefore A3's bound gets violated because A3 has to be, this equation has to be, V31 has to be equal to V21F plus V2F, which means A3 has to be 0, okay? But A3 becomes 0.5, and therefore you pivot A3 with A21F, as A3 is basic and V21F is non-basic. You pivot that, and that by making V2NF to be 0.5, okay? And then you get this assignment, okay? With after I pivot A3 with V21F. Okay. Now here, all the bounds are satisfied, correct? So see, V11 is within its bound, V21B is within its bounds, V31F is within its bounds, and so is V2, all the A11, A2, and V21F, right? So you have, as far as the LP instance of the OR approximation, everything is within bounds. But now we have to check if the solution that you got, indeed, but this is a solution that I got by throwing away all the ReLU constraints. Now we have to check independently if each of the ReLU constraints are satisfied. Now that is a local check, okay? So which you could do efficiently, even if there are millions of ReLU nodes, because all I'm doing is checking if every pair of ReLU pair satisfies that max equation that I showed you. Okay, obviously you will see that there is something broken. Okay, because V21F is 0.5, whereas V21B is 0, while this solution that I got satisfies the LP problem, but it breaks the ReLU pair, the first ReLU pair here. Okay, that check can be done easily, right? Because that's a local check with respect to the solution that the LP you got from the previous LP instance. So here there are all variables are within bounds, but the ReLU pair is broken because V21F is not equal to max of 0 and V21B. Now, there are two ways to fix this, right? You can either change V21B to 0.5, or you can bring V21F to 0, okay? So that is what. So what Reluplex does is it adds a couple of new update rules to the simplex rules that I showed you earlier. And this corresponds to updating only the ReLU, the ReLU pairs, okay, to update the forward and the backward thing to fix it. Let's suppose that V21B is changed to 0.5. Okay, then you will see that if V21B is changed to 0.5, A1 will violate its bound because this equation will not hold good anymore. Okay, A1, right? And therefore you will have to now pivot A1 with V11. If I do that, then I get this. Okay, so A1 moves into the non-basic set with V11 going to the basic, and then you fix. This is a simplex step. Okay, the pivot operation, and you get this. Okay, yeah, but you still have A2 violating as a result of that. So now you pivot again. Okay, after you fix this. Okay, so what you A2 violates its bounds, and therefore you pivot A2, which in this case is B2 to B. And what you now get is, okay, all variables are within the bounds. This is what? This is the table that you that you get, and there and all the ReLU pairs are satisfied too. You can check. See, V22 of F is 0, but V21 of F is, sorry, what is V22? V22 of F is 0, and because V22B of is minus 0.5, okay? I mean, I'm not going through the simplex step, but after, believe me, that after pivoting A22, V22B, this is what you get, okay? The stable shown in here. And now all the ReLU pairs, I mean, there are no broken ReLU pairs because V22F is max of, it is 0, and because V22B is negative, so is, and V21B is 0.5, so is V21F, okay? And so you see, you were able to just do repeated LP calls and interspersed with fixing ReLU pairs. Okay, by fixing ReLU pairs, I mean you're adjusting the input-output, either the input or the output of the ReLU pair variables, so that they satisfy the ReLU constraints in a local way. Then rerunning LP instance, and in some cases you can get without actually case splitting. Okay, so that is the idea. And the reason that thing happens is because with V21B being greater than or is equal to 0, all permissible input values are indeed sat in this case, because if V21B is greater than or is equal to 0, the other branch never contributes anything. Okay, and in some cases, you can get away without actually doing the case splits using over approximation and just locally trying to fix the ReLU constraints. Okay. Yeah. Now, as I said, I mean, so that is basically what Reluplex does. Okay, and you can ask the question: could an SMT not an SMT solver have also avoided this kind of a case split? Like I said, that depends on SAT solver heuristics. But like Arpan pointed out, the problem is NP. So in the worst case, both of them can be exponential, in the sense you can always have pathological instances where they're both exponential. But Reluplex appears to perform better for a lot of DNNs when you directly use Z3 on this thing. Okay, and you will see when you get the assignment on Marabou, you will be comparing some small examples on both Marabou, which uses Reluplex, and Z3. And this paper also has a section on experimental results where they show that on a significant case study, the Reluplex algorithm works correctly. I mean, works better. Yeah. So in addition to the rules that I showed you, these simplex rules, what Reluplex procedure does is it has these three additional, I mean, these 4 additional rules. Okay. The update B and update F are the rules corresponding to that you would use to fixing broken ReLU pairs. Okay. So you update these, you fix broken ReLU pairs only when either the forward ReLU variable or the backward variable are in the non-basic set. Okay, so if xi is in the basic set, and if xi xj corresponds to the input and output node of a ReLU pair. And if xj, the output, is violating the ReLU constraint, and this is applied only when you have alpha xj is greater than or equal to 0, then you fix the input, okay? The input, which is in the non-basic variable, so as to make it equal to its output, okay? So you may need to increase the input to do that, okay? Similarly, if you can also fix the output of the ReLU pair. But the constraint is you will have to do only as long as either the ReLU pair variable, the variable that you fix is in the non-basic set. Okay, so xi xj, if the output is non-basic, and if this is the ReLU pair, and then the ReLU constraint is being violated, then you just fix it. As you can see, that this, if both of them, both the xi and xj happen to be non-basic, then you can use either of them. But the first one you can apply only when the output is greater than or equal to 0. And the second one can be applied when the output is negative as well. Of course, the output of a the kind of scenarios that you so when there are two kinds of scenarios possible for a ReLU, a pair to be broken. Okay, one is that depends on the two scenarios. One corresponds to when the output is greater than or equal to 0. If the output is greater than or equal to 0, the LP on the over approximated model assigns the output to be greater than or equal to 0, but it makes the input, the satisfying instance makes the input not to be something different than max of 0 and VB, that if VB is such that it is not, the max of 0 and VB is not equal to VB, then you can use, in this case, you can either use, you can bring down the output variable or increase the input variable. So you will be able to apply either update F or update B. But if the LP happens to assign a negative variable to an output of a ReLU node, which is not permissible at all, then you can only apply update F, okay, to fix your VF. Now, there is also this one. What if, you can ask, what if, a ReLU pair is broken, but neither of the input, the output variables in the ReLU pair happen to be in the non-basic set? Then what this, so it introduces a pivot. Okay, then you can pivot any one of your ReLU variables with something else so that to move it into a non-basic and so that you can move it to non-basic set, so that you can make progress with you'll be allowed to use update F and update B. Okay, and finally you add the ReLU success, because even after the LP LP solution that you get satisfy all its bounds, you have to check if all the ReLU pairs, you can declare success only when all the ReLU pairs are okay, and that's why the success rule is replaced with this ReLU success. Okay, so not only does all the variables have to satisfy the respective bounds, but all the ReLU pairs have to satisfy their ReLU constraints. Okay, so in summary, what is the this is not the one, so I'll show you what the strategy for using ReLU. So you run LP solver, you first derive an over-approximated model by throwing away all the ReLU constraints so that you can make an LP instance out of it. Then you run an LP solver like simplex on it. If the problem is unsat, then you return unsat. If not, if it is sat, then you check if there are any ReLU pairs that are broken. No. So if it is, okay, I mean, if it's not unsat, then you run the LP solver on it to get a satisfying solution. If you're able to get once you get a satisfying solution, you have to check that every ReLU pair is no ReLU pair is broken. If no ReLU pair is broken, then you're done. No case splitting or anything, then you return SAT. If one or more of the ReLU pairs are broken, you correct as many violated ReLU constraints as possible using the update F and update B. And if necessary, using the pivot rule, pivot for ReLU rule, okay? It sometimes is needed in order to be able to apply update F and update P. Now, if you can fix all the ReLU constraints without actually introducing any outer bounds violation on any of the variables, then that is the fixing step. If you're able to fix all the ReLUs, then you're happy. You can return SAT. Otherwise, you go to step step 2. But in between, you could be, of course, okay. But in between, if one or more, if you're not able to fix using the update F and update B by changing the forward and the backward, then you have to rerun with whatever that you have fixed. Okay, you can try to get a different LP solution and see if you can fix it with that. Okay, but of course, this loop of going to step 2 and then fixing the ReLU may not terminate, and therefore, in order to make it terminate, there is this thing. So you only run this up to, you try to see if you can fix all the ReLU constraints by running this loop, fixing loop up to a certain bound, okay, which is some ad hoc bound. Okay, you try to keep fixing these ReLU pairs until up to a certain number. If you're not able to do it, then only then you will pick one of the broken ReLU pairs and you split on the condition, on the ReLU condition of that ReLU pair, and you repeat this procedure, the whole procedure. So it's only after trying to see, without actually case splitting, if you're able to fix all the ReLU pairs, a certain number of iterations, then only then you will try to case split. Okay? That is the whole idea. Okay, so that's why I call Reluplex is like a lazy case splitting approach. Okay, on running LP solvers on a LP instance of an over-approximated LP model of your original neural network. Okay, and that's how it is done. So there are lots of things here. You know, how do you choose how many times, well, the n, the bound that you will do, and and which ReLU constraint, if you're not able to fix all of them, which ReLU pair that you split on, and all that is determined by heuristics. Okay, and that's what this thing does. Okay. Okay, these two are, I don't want to discuss that thing. So that is what Reluplex procedure is. Okay, so any questions here? Yeah, I will give some exercises. I mean, it would be good for you to, based on the slides and the procedure given, you just try to simulate. At least what I expect you to do in the Reluplex is, of course, you'll be using Marabou on real examples. That is where you'll be using Marabou as a black box. But I also want you to, on pencil and paper, some small examples that I assign you as part of the assignment, where I want you to simulate this Reluplex procedure by hand, so you will understand how this over approximation, how you're delaying the case split. Okay, uh, you know, to some extent, to see if you can get a solution without actually employing a case split, and that is the idea of here of Reluplex. Okay, any questions here? I'll stop here. Okay. By the way, I know that I'm trying to have a class tomorrow. If Madhukar confirms it is okay for him, there will be a class at 5 o'clock. Okay, because I want to have that makeup class because I am running behind schedule. Okay, I know that I'm still delinquent and giving you assignment. I will give it definitely before you guys take a break for the midterm. And I want you to be at least trying. And there won't be any midterm in this course. Maybe later on there'll be a small quiz later in the thing, but it's very important that you at least devote some time for this course. I mean, for this course by solving the assignment during the midterm break. Okay, and I also want you to pay attention. I mean, to review the paper that is assigned to you a little bit, and then get in touch with me. Or with any of the mentors. If you're shy, getting right away to your mentor, you get in touch with me. But I think you should try to get in touch to see at least once, before the midterm is over, so you will have an idea of what the paper that you will be working on will be. So in lieu of you're not having any midterm exam for this, I want you to, put in that time for you to solve the assignment that I'll be assigning you, and also kind of try to read to see if you are okay with the paper assignment that you have. Okay, that is something that I expect from you. Yeah. Okay. Any questions on what I just now said? Okay, guys. Then if that is the case, then I'm going to stop sharing, stop recording.